Hi everyone, thank you for joining us today on this nice Friday afternoon or morning in the US. Today we're going to be presenting a webinar based on error factors that affect point cloud accuracy, and Sam Souliman, our Senior Support Engineer, will be delivering the content today. I am Paris Austin, the Business Manager for the LiDAR survey team at OxTS, and we'd be really happy to take any questions you've got at the end of the webinar. So we've got 45 minutes scheduled, and we're going to take about 30 minutes to deliver the content and then leave some time at the end in order to take any questions that you might have. In case you haven't been aware, we are also running a series of other webinars, so be sure to go to the OxTS website at some point, and you can see on the resources hub on the web page that we have a series of other topics as well if you're interested in them. So without any further delay, I'm going to hand over to Sam and he's going to deliver his webinar.
Thanks, Paris, and welcome everyone to our webinar on factors that can affect the point cloud accuracy. So a bit of context at the very beginning. As you know, it is possible to realize some very effective mobile LiDAR scanning systems or mobile mapping systems by integrating LiDAR scanners with INS devices. And the reason why it is recommended to use INS as opposed to GNSS only devices is that INS is capable of giving you more accurate data, and especially giving repeatable navigation data. We will see the importance of that in a minute. So OxTS has been in the business of producing INS devices for more than 20 years now, and we are bringing this expertise into the mobile mapping systems now. Okay, so factors. We will be looking at a number of them. There's 8 factors that you can see listed over here. So position accuracy and orientation accuracy of the INS, the Boresight alignment between INS and LiDAR, distance to target, speed of travel, RPM rate and angular resolution of the LiDAR, range accuracy and mounting angle of the LiDAR. We will look at each of these factors individually, but as we will mention time and again, these factors are to be considered interdependent. Their impacts are always correlated. They can add up, they can amplify the impact of one another, but at the same time, it's also possible, if used properly, to use one factor or some factors to mitigate the negative impact of other factors. We will see examples of this as we go. Okay, first of all, position accuracy of the INS. The INS is obviously responsible for providing the data required to georeference the LiDAR data. Without a position, without an orientation, the LiDAR data is basically meaningless. This means that an error in the position that the INS provide will translate into wrong position of objects in the point cloud. The objects that are surveyed by the LiDAR will be placed in the wrong position. Having an accurate position is fundamental to have a repeatable data. In the sketch that I have here on the right, the idea is that the vehicle is passing twice in exactly the same spot, but because the position is not very accurate, the position is reported as being different. And because the LiDAR data will be the same object will be placed in 2 different, maybe slightly different, sometimes it's going to be a large difference between the 2 positions in the point cloud. So that can cause distortions, even double visions in the point cloud. We will have some examples. First of all, that's a test that we have done with some reflective strips put on barrels, as you can see here on the left. And then what we've done is setting the reflectivity threshold so that just the reflective strips would be visible in the point cloud. And here are 2 examples. On the left here, we have the RTK scan. So this is a scan done with RTK position accuracy. As you can see, you can definitely identify the barrel here, all the reflective strips around it are clearly visible. The contours are correct. On the right, that's a scan done in SPS position accuracy. We've done several scans, several passes, and every time we've scanned the barrel, we would have a different position. So as a result, this is a scan that was particularly bad, if you wish. We had basically 3 barrels on top of each other. So that's a it's not always this bad, but it's quite an example of what a very bad position accuracy can cause. Other examples. So these are a couple of scans, a couple of passes of the same buildings done in 2 opposite directions. So on 2 sides of the road. And as you can see, the image is blurred. And if you look at the lamppost on the left, you can see 2 of them. Whilst obviously there was only 1 lamppost. You can compare this with the result of a single pass in SPS mode. So as you see, because the position accuracy is not ideal, it is difficult to put together the 2 scans. They will not overlap because of the inaccurate position. So looking at this, you might think that even if you don't have a great position accuracy, just by avoiding multiple passes, you can get away with it. So this is only true if you do not care about absolute position accuracy. Another example here, we have 2 point clouds on top of each other. The blue one is obtained with RTK position accuracy. The red one is obtained with SPS position accuracy. So you can see that the red lamppost is not in the same position as the blue one. There is a shift to the left and down. That is because the position of the INS was not very accurate, not as accurate as when the system was in RTK. So if you care about absolute position accuracy of all the objects in the point cloud, you need to consider that a high position accuracy is required. You can compare the result with this. This is a point cloud that has been obtained in RTK position mode, or position accuracy for the INS, with 2 passes. So unlike the point cloud that I've showed you before, you can see that in this case, the 2 scans are perfectly overlapping. And we have a neat vision in this point cloud. You can see that the lamppost is one nice single one. So that's for the importance of the INS position accuracy. How about obtaining that? Well, first of all, you need to apply differential corrections in order to get a RTK level, so high position accuracy. Another important thing is to put the INS in the best possible conditions to perform. So that means correct settings, correct configuration, and warm up, so you can get the best out of the INS. When post-processing, I would recommend you post-process in combined mode, and that is because this will give you a higher position accuracy compared to the simulated processing mode. If you really cannot get high position accuracy, you don't have availability of differential corrections and so on, then definitely try to do just single passes. Because as we've seen in SPS mode, more scans of the same objects will not perfectly overlap. Obviously, having single passes will not be always possible or always desirable. So if you have to do multiple passes, having high position accuracy is absolutely fundamental. Okay, next, orientation accuracy of the INS. Again, the concept is similar. Because the INS data is the one used to georeference the LiDAR data, any error in orientation of the INS will translate into wrong orientation and position of the objects in the point cloud. This can cause distortions and blurred vision. Again, the sketch on the right, the idea is that you are scanning the same object, but because of angular inaccuracy, it will be placed in slightly different positions when surveyed by the LiDAR and getting the reference data from the INS. And an important aspect to mention is that with all angular inaccuracies, and obviously orientation is one of them, the errors will be more visible the longer the distance from target is. Distance will amplify the error that you get from an inaccurate orientation. Examples, again, our barrels. So over here we have a scan obtained with a high orientation accuracy. With a less accurate orientation, you can see that you can still identify definitely, the contours of the barrel, of the reflective strips around it, but the data is noisier. It's not as neat as the first one. And by putting them on top of each other in the same point cloud, you can see that there is a shift to basically towards the top of the barrel that was surveyed with a inaccurate orientation. Okay, so it's not just about the noise, it's also that the objects are placed in basically a wrong position. Other examples, this was surveyed with a lower orientation accuracy. So if you focus on these two signposts on the right and also on the fence down here, that's the result that you get. And you can already see that the image is a bit noisy, it's a bit blurred. So if you compare it with this one that was obtained with a high orientation accuracy, you can see that the signposts are neater, are thinner, because there is less noise around them. And the same for the fence. It's neater, thinner, compared with this one. Because the lack of orientation accuracy will add noise to your point cloud. That is because the hits will not be placed properly in their exact position. So things that you can do to improve the orientation accuracy. Again, put the INS in the best conditions to perform. So correct settings, correct configuration, and proper warm-up of the unit. If you require high level of orientation accuracy, then definitely use higher grade units that will be equipped with higher grade IMUs, which will mean that they will have a better orientation, more accurate heading, pitch, and roll angles, such as the Survey Plus that OxTS provides. And again, post-process do INS data in combined mode because this will improve the orientation accuracy. Third factor, the Boresight alignment between INS and LiDAR. So the alignment means knowing exactly the angles between the two. So what causes issues is obviously the lack of alignment or misalignment, if you wish, between LiDAR and INS. And even a small misalignment, we are looking at half a degree, can cause a significant distortion in the point cloud. Even depending on the level of accuracy that you are looking at, but even a 0.2 or 0.3 of a degree can give you a significant impact. And again, because it's an angular kind of inaccuracy, distance will make these more visible. It will make the errors worse at the longer distances. So what the Boresight misalignment causes is for objects to be seen in a different way depending on the position and the angle from which they are being viewed or seen or scanned by the LiDAR. So if you have a building, this black rectangle here, that is a top view of a building, imagine that. When you survey that traveling in different directions, because of the Boresight misalignment, you will have that building being placed in two different positions. And when you try to put everything together, you will not have a neat result, but instead you will have a blurred image or even a double vision if the misalignment was very, very bad. Examples. So that's an example of double vision. These are two scans in opposite directions. And as you can see in the middle here, we have two lampposts. That's one lamppost that was, collocated in this position when the vehicle was traveling, say, to the right, and the red one is when it was traveling to the left. So they cannot perfectly overlap because of the Boresight misalignment. So you end up having a double vision. Another problem is the position offset. In this case, we have 2 point clouds on top of each other. The blue one was obtained with a proper Boresight alignment. The red one, it's the same that you can see here. That's this red lamppost here. So it's a single pass. And because it's a single pass, you don't have a problem of a double vision, but what you have is an offset in position. In a similar way to when we've seen the SPS scan, in this case, because you have a misalignment, because you have an error, in the orientation of the system, the position of the lamppost is not correct. It should be on top of this blue one, and it isn't, even with a single pass. Again, compare it with what you would get with a system that has been properly Boresighted. That's 2 passes with a proper Boresight alignment. So the 2 scans are perfectly overlapping, perfectly on top of each other, and you have one single lamppost, and the image is neater. So how can you get a proper alignment? Through a Boresight calibration procedure. And we have a software or OxTS georeferencer that can do this for you. So what you need is just to collect your data, complete appropriate maneuvers to collect Boresight data, and then the software will put everything together and will tell you the exact alignment, the exact angles between your LiDAR and your INS. That's another example of what the software does, basically, of the results that you can get from it. If you imagine surveying a road traveling into opposite directions, say north and south, and surveying a building, what you can end up having without a Boresight is the 2 scans not perfectly overlapping. As you can see here, the red and the blue line. That's a cross section of the road, and on the side you can see the building. So by Boresighting the data with our software, this is what you get. The 2 scans are perfectly aligned. So the software doesn't put together the 2 scans. The software aligns the LiDAR to the INS, and as a result, when you process the data, you can have a neater result. Okay, distance to target. It has basically 2 main effects. One we've already mentioned, and that is to amplifying the errors resulting from angular inaccuracies. The other effect of distance is that at longer distances, you will have a reduced point density of the point cloud. Examples, again, with our barrels. Right here, center left, you can see the neater target, the one that was surveyed with a proper Boresight alignment in RTK mode. Then again, we've seen this, that is the less accurate orientation result. But if you have a orientation that is not ideal already, and on top of that, you survey the target from a longer distance, this is what you get, a blurred image of the barrel. And that is to show that distance will act on angular inaccuracies and amplify them and make them worse. So what can you do to mitigate the impact of distance to target? Obviously, in many cases, you won't have a choice. The distance is what it is, and you cannot simply get closer to the target. This will not be always possible. So what you can do, because as we said, distance will act on angular inaccuracies, is limiting the errors by getting the best possible angular accuracies through high INS orientation accuracy, higher grade IMUs, and also through a proper Boresight calibration procedure. So you remove the best part of what distance will use against you. Also, you can limit the loss of point density by increasing the LiDAR RPM. You can also reduce the speed of travel. And you could also survey the same target more than once, provided you have an accurate position and accurate orientation. Otherwise, you can have issues with multiple passes. Also, another way of increasing the point density is by having a LiDAR that has a larger number of beams, a larger number of channels available, in combination with likely mounting it differently, so you can exploit the increased number of beams. Speed of travel. So speed of travel doesn't directly affect the accuracy of the point cloud as such, meaning it doesn't cause objects to be placed in the wrong position. But what it does is affecting the point density of the point cloud to the point where it can cause gaps in the data, the point cloud. So you can see this example here. The picture at the top is obtained with a LiDAR that was scanning the road, so pointing down, and the vehicle was speeding, so increasing its speed from 0 miles per hour down here on the right up to 20 miles per hour on the left. So as the vehicle was traveling right to left and increasing its speed, you can see that these gaps, these black gaps here, are widening, becoming wider and wider as the speed increases. While down here you can see that with an average speed of 20 miles per hour, the result was perfect, no gaps, even with the same speed that caused issues at the top. So that is an example of when you do not have enough hits on the targets that you want because of the speed, you can get gaps in your data. Another example, these are reflective strips that were placed on the ground. So again, the LiDAR was pointing down while surveying. And you can see that at lower speed on the left, you had more hits on the strips. So point density is better than what you can see here on the right. Fewer hits because of the higher speed. So basically the LiDAR had less time to scan these strips. So what can you do to mitigate the impact of speed of travel? The first obvious choice would be to increase the LiDAR RPM. In this way, you can increase the longitudinal or directional, in the direction of travel, resolution at the expenses of the lateral one. So if you are not interested in surveying what is on the sides, for example, but just the road, then you could do that. Another thing that you can do to increase point density is scanning the same targets multiple times. Again, if you do this, you will require a high position orientation accuracy. In some cases, you can use a LiDAR that will have more beams and utilize a different scanning position. If we go back to this example, if you imagine the LiDAR, as I said, that was pointing down, if you imagine the LiDAR being mounted higher up on the vehicle, so more distant, from the ground, the result will be that the LiDAR at every scan will be viewing a larger portion of the road, because the same angle would be covering a longer distance, projected on the ground. So as a result, instead of having these condensed gaps, what you would have is these gaps spread more evenly on the road surface. So you would have basically an increased distance between scan lines. If at this point you can have more beams, so more scan lines, say 32 instead of 16, you would at that point halve that distance. So that could be a way of doing that. You could benefit from having a LiDAR with more channels, provided you use it sensibly. You just don't use it, in exactly the same way as you would use a LiDAR that has fewer beams. Related to this, as we've already discussed, the mounting angle can also mitigate the impact of speed of travel. If you select the proper mounting angle, depending not just on your speed, but also on what you are surveying. So where are the objects that you want to survey? You can optimize your mounting angle in order to have the larger number possible of hits on your targets. It has to be kept in mind, though, that whenever possible, lower speed should be preferred. Whenever possible. Obviously, this is not always possible. But because, as we mentioned, all the factors will be correlated, you can use a lower speed to mitigate the impact of other factors that you cannot do anything about, such as, for example, distance to target, which is another thing that will reduce the point density. So if at least you can act on one of them, you reduce the impact on your point cloud. Okay, RPM rate and angular resolution of the LiDAR. These two are always related. So an increasing RPM rate will correspond to a worsening angular resolution. This is because the LiDAR, if it has a higher RPM, basically it means that it will be spinning faster. By spinning faster, it will have a larger angle between two successive pulses. And that angle that you have is basically your angular resolution between successive pulses. So for the VLP16, for example, if you have rates of 3, 6, and 1200, they will correspond, linearly to an angular resolution of 0.1, 0.2, and 0.4 degrees. The RPM goes up, higher point density, the angular resolution becomes worse. Examples, again, our barrels. In the center, you can see this scan done at 300 RPM. On the right, that was done on 1200 RPM. So in this case, there was no real benefit of using a higher RPM. Like even point density is not tremendously better. And that is because this scan, the 300 RPM one, was already done at a close enough distance, 10 to 15 meters, and traveling at low speed. So point density was already okay. There is no real benefit in increasing the RPM in this case. There is, though, a downside, which is missing the vertical lines. These thin reflective strips that were placed vertically, they are visible in this scan. They are not visible basically, or almost completely missing with the 1200 RPM, and that is because you have a more coarse angular resolution. So these strips are too thin for the LiDAR to detect. Other examples. This was done at 300 RPM, so you can see a low point density. If you look at the fence over here, there are some missing bits. Also on this pylon, there are some missing bits. The point density is not very high. Compare it with this. So same scan, but at 1200 RPM, you can see that you have more hits on the fence, on the tree, and on the pylon and lamppost. But also, you can notice that the image is a bit more noisy. So you have more stuff, more flesh on the bones, if you wish, but not as neat. Look at the contours of the tree. In this case, they are very well defined. In this case, yes, you have an increased point density. You see the image is more dense, literally, but the contours are noisier. If you look at the fence, at the lamppost, at the pylon, the data is noisier, but it is more dense. So it's basically a trade-off. Right? Depending on what you are trying to do, there will be the right balance between higher point density without compromising too much on angular resolution. If you increase the RPM, you have higher point density. This will be at the expenses of the LiDAR being less able to detect thin objects, and also you will have more noise, so object will be less well defined. Range accuracy of the LiDAR. So every LiDAR will come with the given range accuracy, and this basically causes surfaces and objects that should have just 2 dimensions to show a third one, a thickness or a depth that they do not actually have. This thickness can vary, between few and several centimeters depending on the LiDAR model and the range accuracy that comes with it. So a couple of examples. On the left, you can see a target that we use to Boresight to do our test. It's basically reflective strips placed on a wooden board. So we collected some data and set the reflectivity threshold very high, so only the reflective strips should be visible. And obviously they are flat, they are not thick. They should be maybe 1 millimeter, so you wouldn't expect the third dimension, the depth, to show up in the point cloud. But instead what happens is that you do see a layer of 2 centimeters, depth, if you look at it from the side. That is because the limited range accuracy. Same concept here with the barrels. This is a top view. So again, the strip should be thin, almost not visible from the top. But what happens when you start having tens of thousands of hits, the distance between the LiDAR and the barrel or any target will not be measured always exactly in the same way. You will have 2, 3, 4 centimeters difference. And when you have thousands of hits, this will build up into having a layer that can be, like in this case, 3 centimeters thick. Okay, this is down to the range accuracy of the LiDAR. Obviously, it will combine with other factors such as orientation and position accuracy. So there is not much that you can do about the limited range accuracy itself, other than getting a different LiDAR with a better range accuracy, but obviously this is not always possible or desirable. What you can do is acting indirectly on it by limiting the impact of all other factors that we've discussed, so that the limited range accuracy doesn't combine with other factors to make things even worse. You try to isolate it, say, and make sure it doesn't cause too much of an impact. If you really care of absolutely high level of accuracy, then you probably need to consider having a higher grade LiDAR as well. Okay, finally, the mounting angle of the LiDAR. So a LiDAR will have a limited field of view that is typically 360 degrees horizontally by 30 or 40 degrees vertically. The way you mount the LiDAR will determine what it can see, basically. So, how that limited field of view will be used, which objects, depending on where they are relative to the LiDAR, can be seen, can be hit by the beams, and also at what angle of incidence that is going to happen. All of this will impact the density and the accuracy of your point cloud. So we have a couple of examples here. In the first case on the left, you can see the LiDAR that was mounted on the rear windscreen of our vehicle, tilted by about 45 degrees. In this other case, that was mounted on the roof of the car, the front part of it, and tilted forward by about 10 degrees. Which one is the best? So that will depend on what you are surveying. In this case, we have reflective strips. We've already seen this. So that was obtained with the LiDAR tilted 45 degrees off the back of the vehicle. While the data collected with the LiDAR, in the front, tilted by 10 degrees, was not as good. You can see, a huge difference in the point density between these two cases. But then when surveying the barrels, you can see that this time around, the 10 degrees in the front had a better result. It's a cross section, had a better result than what you had having the 45 degrees off the back of the vehicle. Because in this case, the LiDAR had less time to hit the barrel as the vehicle was passing, by the barrels. But when tilted just by 10 degrees, it exploited its field of view in a better way. So there is no fixed rule. it will depend on where the objects of interest are. You know, is it the road surface? Is it objects that will be on the side, and so on? And also, it will depend on the shape. Are they large objects? Are they very thin objects? What you want to do is to maximize the amount of time the target will be exposed to the LiDAR. And in order to do this, you need to give your consideration to the speed of travel that you plan, of using, and the expected distance to target, so that you can ensure a suitable point density. Depending on these factors, and as we mentioned several times during this presentation, factors will interact with one another. So depending on, in this case, especially speed of travel and distance to target, you want to consider that to select the best mounting angle to maximize the point density of your point cloud. Okay, thank you.
Okay, thank you very much, Sam. So if anyone has any questions at this point, as a result of the content that Sam's presented, then please do enter them into the chat window on the right. Otherwise, it's well worth checking out the website and the resources hub to see some of the other webinars that we're putting on, but also on the support site at support.oxts.com. There's a lot of resources there relating to how to configure a Velodyne LiDAR, configure a ZNF LiDAR, and some other useful technical articles as well. So we currently do not have any questions waiting to be answered. We have one now. The question is the 45-degree angle on the back of the car, is the 45 degrees relative to the ground or something else?
Yes, in that case, let me see if I can go back to the image. Here we go. If I can go back to the image, yes, that is relative to the level, so to the horizontal. Okay, that is about 45 degrees.
Okay, thank you, Sam. And that, because that LiDAR has a plus minus 15 degrees field of view, that means that its field of view relative to the horizontal will be effectively minus 30 to minus 15 degrees. So you're predominantly focused on the road surface with that setup. Also, it will scan the sides of buildings very well as you drive through the area. Okay.
Yep.
No more questions currently. Oh, one more question has come in. How does accuracy depend on beam divergence?
Well, it won't necessarily. So the beam divergences will basically determine two things: how wide the angle is, basically, between the first and the last beam, if that makes sense. So that will determine the angle, and consequently will determine the linear distance that the LiDAR will be able to hit, when it meets a building or the ground. And it will also have an impact on how neat the contours can be. Okay, does that answer the question?
I hope so. If not, then please do let us know and we can maybe answer the question in an email instead. There's a couple more questions. Which other LiDAR will work with OxTS georeferencer?
Okay, so that
Shall I answer that?
Yeah, that's a question for you, Paris.
So in the short term, we're looking at some other entry-level LiDAR systems that are very popular at the moment. So we're looking at the Ouster LiDAR product range and also a Hesai LiDAR. And we have integrated the hardware with ZNF laser scanners, and also our data format is supported by the Regal data scanner, laser scanner. But with both the ZNF and Regal as examples, they both have their own post-processing solution. So OxTS have not developed the georeferencing solution for those systems. If we we have the requirement for it from customers, then we'd be very happy to have that conversation. But at the moment, we're focused on the LiDAR sensors that do not come with their own post-processing offering. So we're hoping to fill that gap for customers. There's one more question, Sam, about have we explored SLAM to derive the orientation biases?
So we are doing some work on using the LiDAR as a source of aiding to the IMU navigation solution. This is as far as we've gone at the minute. You know, with our newer models, we have what we call generic aiding, so you don't have necessarily to use GNSS to integrate the IMU solution. You can use other ways of providing navigation data, and obviously a LiDAR would be something that can help in determining the position and the orientation of the system. But it's still pretty much at, I would say, at the beginning of the testing phase.
Yes, very much so. And there's a number of SLAM algorithms that are available on the market, both open source and commercially licensed. But what we have discovered is a lot of them will have limitations in terms of the orientation or the vehicle speed at which they will work. So they are very tailored to a given application and don't work as flexibly as GNSS plus IMU does in terms of navigation. So we're aware of SLAM as a concept for navigation and improving our point clouds, but at the moment there's no one solution that we believe is suitable for all customers, but we're certainly looking into it. Okay, there's no more questions, then we're 3 minutes from the time running out, so we'd like to thank you all for joining today. And thank you, Sam, for presenting. And if any of you would like to have this recording, it will be sent round in 24 hours time. So you'll get an email linking to the recording. But if you have any specific questions, then just be sure to send us an email and we'll get back in touch as soon as possible.
Yeah.
And have a nice weekend. Thank you very much. Goodbye.
Bye.